When it comes to electric vehicles, the first company that comes to mind at this point is Tesla. That's because Tesla, even with a slightly slower year for 2024, remains the best-selling EV company in the entire world. Their Model Y is the best-selling car of any type globally, and when all cars are included, they sell more electric cars than anybody else. On top of this, Tesla also sells stationary storage products like their Powerwall and MagBak. All in all, they end up being one of the world's largest producers of batteries, both directly and indirectly. But just how big is that scale? Today, we're breaking down Tesla's massive battery production operation, how they're made, who makes them, and how many batteries they make per second. So let's get into it. To start, let's break down a quick history of electric vehicle batteries. Back in 1801, the first battery of any type was introduced. This was introduced by Alessandro Volta and had a very simple design. Over time, things developed, and then the first electric car was actually produced in 1832. Yes, 1832. That was invented by Robert Anderson, but it wasn't until around 1890 when the first successful electric cars debuted. In 1900, electric vehicles actually accounted for 1/3 of all vehicles on the road and continued growing in sales. At the time, cars were still growing in popularity, so electric cars were popular since they were easy to operate, didn't emit pollutants, and could be recharged at home, which was becoming more common in the 1910s. In time, the internal combustion engine ended up replacing electric vehicles, so certain developments stalled, as vehicle ranges and capabilities grew with the internal combustion engine. In the 1970s, however, lithium-ion batteries were introduced, offering a higher energy density and lighter weight. The story of Tesla Motors really originates with the AC propulsion T0 prototype created in 1997. This was a fully electric vehicle that, thanks to being so light, had some amazing specs right out of the gate. A 0 to 60 in 3.6 seconds and 200 miles of range. Ultimately, that car is what led to the Tesla Roadster, which launched in 2008. This car was built using Panasonic 18650 battery cells, organized into modules, which were then assembled into a single big battery pack. For the Roadster, about 6,831 individual battery cells made up its battery pack and delivered its specs of 0 to 60 in 3.7 seconds and 245 miles of range. This started around $100,000 and then grew in price, but was huge for the beginning of Tesla and the entire EV industry. From there, Tesla created the Model S, utilizing the same battery cells supplied by Panasonic. At launch, this car utilized about 7,104 18650 battery cells, but over the years it has gone through many different battery configurations. Today, Tesla only sells the long-range and Plaid Model S, but over the years they sold many different types and even labeled them based on pack size for a time. Pack size is labeled in total kilowatt hours, but that is of course spread across thousands of battery cells. For battery cell type, the number indicates their dimensions. The first number denotes the diameter in millimeters, while the second indicates the length. So an 18650 battery cell is 18 millimeters in diameter and 65 millimeters in length. Other cells like the newest 4680 cells we'll talk about later follow this naming, 46 millimeters in diameter, 80 millimeters in length. In any case, the Model X was built on this same platform, and then Tesla introduced the Powerwall in 2015. This is a home stationary storage product that backs up electricity for your home and works great storing up excess solar to use when the sun isn't shining. Today they are on version 3 of this product, and this actually contributes a lot to their yearly battery production. In fact, it's estimated that each Powerwall, of which multiple are typically installed in a home, uses about 4,288 battery cells. For the future, this could all change quite a bit as they rework products all the time to interface with various battery cell types based on supply. Personally, I expect future Powerwalls to mainly utilize LFP chemistry batteries and potentially shift to 4680 cells, but that remains to be seen. Of course, the larger the cell, the less required for the same energy, which ultimately reduces complexity and cost. For a while, that 18650 was the main battery cell for Tesla, but the real change to battery cells came when Tesla introduced the Model 3. The Model 3 was designed to be Tesla's first true mass-market, more affordable vehicle. As such, they introduced it with a brand new platform and new battery cell type, 2170. These batteries would be produced in a joint venture between Tesla and Panasonic at their massive dedicated battery factory, Giga Nevada. It's called a Gigafactory because they produce over 1 gigawatt of battery storage at that factory each year. In fact, at Giga Nevada today, they produce about 37 gigawatt hours annually. The Model 3 has changed a lot with its battery pack over the years, but on average, today it's estimated that the Model 3 ships with around 2,976 cells for standard range, or 4,416 cells for long range. Again, these are 2170 battery cells, so for a smaller pack, with each cell having more capacity, the number can decrease a lot from the Model S's 7000 cells. Ultimately, the capacity is what matters there, but it's interesting to see cell counts regardless. A vehicle like the Rivian R1T today uses about 7,776 2170 cells in the large pack, and they round that up to 7,777 with a flashlight in the door. Up until this point, before about the 2020s, it was fairly easy to track Tesla's battery supply. For the most part, it was coming out of a single joint venture factory. However, with the introduction of Tesla's second factory, Giga Shanghai, in 2018, and the launch of the Model Y in 2020, things started getting a lot more complex and scaling much further. Around the same time as well, Tesla introduced the MagBak, with first installations in 2020. The MagBak is Tesla's utility-scale energy storage product, specifically designed to stabilize electric grids. As you can imagine, each battery is filled with a massive number of battery cells. In fact, a guesstimate there, if utilizing a similar chemistry and density to the Powerwall, is that each MagBak uses about 1,238,756 individual battery cells. This could be quite inaccurate, as Tesla does not disclose this detail, but still, it gives you an idea of the scale of this product. Production of MagBaks has scaled up massively as of late, thanks in large part to Tesla's Lathrop, California factory dedicated to this product exclusively. From here, production is only expected to grow, and it's in large part thanks to battery cells from their supplier CATL, who has become the largest battery manufacturer in the world. CATL supplies that mega factory, and Tesla assembles MagBaks there in growing numbers. More about CATL later. It's a really impressive product, but interestingly, one that most never really see in person. It's kind of the polar opposite of the Cybertruck. It's very hidden. Back to cars though, Tesla's Giga Shanghai went from groundbreaking to production in less than a year, and since then has become a powerhouse for Tesla. They started simply by selling the Model 3, but in time grew a lot from there. In fact, they grew so much that we've seen the introduction of the refreshed Model 3 and Y come out of that factory first before any other factory. Tesla sells many cars in China, but also uses that factory to produce the Model 3 and Y for many European countries. As such, that factory needs a significant number of battery packs, and one thing Tesla is always keen on is lowering production cost. One big way to lower production cost is to localize parts sourcing. So today, out of Giga Shanghai, the Model 3 and Y utilize an LFP chemistry battery cell from CATL that is also in a prismatic form factor. That's for standard range cars, and then for long range models, they use normal NMC chemistry produced by LG China. The thing to note here is that those suppliers make the cells themselves, but then Tesla assembles the battery packs at their own factories to organize those into the proper pack for vehicle installation. That typically happens at the factory assembling the cars, except in the case of Giga Nevada. In 2020, Tesla held their Battery Day event. In that presentation, they outlined their plans to make more affordable battery cells in the future, ultimately halving the cost per kilowatt hour. They would do this with a new cell design, 4680, a new cell factory, and improvements to anode materials, cathode materials, and cell vehicle integration. One big innovation here they outlined was the wet process used and how their dry process would massively reduce complexity via a 10x footprint reduction and 10x energy reduction. There was a lot more talked about this event, but ultimately they said this would lead them to being able to produce a $25,000 passenger vehicle. They also said that this would enable high-end long-range cars like the Plaid Plus Model S, which unfortunately didn't end up coming to be. That event though, and especially the $25,000 vehicle, was very exciting and had a lot of people waiting to see this technology in new cars. The Model Y, for instance, was set to get 4680 battery cells utilizing the new structural battery pack, but of course, this is Tesla. Almost everything talked about at this event has been progressing, and we even recently saw a prototype Cybertruck that used that dry cathode process, but everything has been heavily delayed. They had planned to scale up quickly and introduce this new technology in the Model Y out of 2 new factories simultaneously. While Tesla did announce their own battery cell production plans at this event, which would seem to go against suppliers, they were clear that this was only to add on to the supply that suppliers were giving them to help scale. Of course, though, they couldn't stop and wait for the 4680 battery to fully arrive, which is part of why we saw their relationships with suppliers continue to grow. Also a footnote, Drew Buglino, who was the primary speaker at this event, did end up leaving Tesla in April of 2024, as Tesla focused more on autonomy. From there, Tesla didn't slow down. The Model Y first rolled out of Giga Shanghai in January of 2021, but by March of 2022, the Model Y was also shipping out of Giga Berlin. This was their entirely new factory, and at the time, both this factory and their new Giga Texas factory were supposed to start producing what was deemed the Model Y 2.0. Giga Texas rolled out first Model Ys in April of 2022 at their Cyber Rodeo event, and proceeded with deliveries a few weeks later. This was that new 4680 Model Y, but this particular configuration didn't actually last long, as I mentioned. This was supposed to be a new Model Y utilizing everything Tesla announced at Battery Day. A structural battery pack, 4680 battery cells made in-house by Tesla within that same factory, and more. In practice, Tesla did ship a certain amount of 4680 Model Ys out of this factory with that new technology, but ended up shifting completely to the same 2170 cells that they launched it with. Their own production and scaling of 4680 cells took quite some time, and saw many delays, which is why that whole plan shifted. In fact, it shifted such that in time, the Model Y out of Berlin began utilizing a different blade-type battery produced by BYD for the standard range Model Y. The long-range version from that factory uses batteries from LG China. As far as we know at this point, Tesla isn't making 4680 cells at that factory at all. But then we have the Cybertruck. In 2019, Tesla announced the Cybertruck. It was a crazy product that most believed would never ship, but sure enough, Tesla shipped first Cybertrucks at the end of 2023. Of course, after years of delays. As it turns out, at least part of those delays was because of the battery tech Tesla needed to ship this truck with. Throughout 2024, Tesla scaled Cybertruck production and shipped just under 40,000 of them. But the unique thing about the Cybertruck is that it is only ever shipped with one type of battery, Tesla's 4680 cell. Originally, this battery was produced at Tesla's Cato Road pilot plant in California, but in time ended up being produced as Tesla originally intended, at the same factory that makes that car. That means that there's no transportation, and cost can be driven down internally. It's kind of the ultimate vertical integration, once cost comes down to be on par with experienced suppliers. In practice as well, this was the second version of the 4680 cell that brought improvements from their version 1 shipped on some Model Ys. The first big improvement came with weight, down to 49 grams per cell from 70 grams thanks to an optimized thinner shell. In practice, they reportedly filled the extra space to improve pack density by about 10%. For the Cybertruck, its design is reliant on this battery, and its structural battery pack in particular, so Tesla's scaling of the 4680 battery was ultimately a piece of this truck's delays. Today, though, they have scaled up well on 4680 batteries, and depending on that technology's growth and Cybertruck demand going forward, we could see these batteries make their way into other future Tesla products. Personally, I expect we may see them on the Cybercab, but that remains to be seen. Tesla celebrated making over 100 million of these cells in September. That sounds very impressive, but soon we'll see how much that is just a drop in the bucket, given Tesla's massive global scale. With thousands of battery cells per car, you end up needing billions to deliver millions of electric cars. So far, we've talked a lot about different types of batteries Tesla utilizes, but of course, they aren't the only EV maker out there. Lately, of course, more and more automakers are entering this space in order to compete with Tesla, but some have been around and shipping consumer cars just as long as Tesla. Take Nissan, for example. Nissan actually made their first electric vehicle back in 1947. It was a pretty popular car until oil supply stabilized, so their next effort came in 1996. The Prairie Joy EV was actually the world's first EV equipped with cylindrical-type lithium-ion batteries, but Nissan's big entry into EVs came in 2010 with the Leaf. The Leaf was the first mass-produced electric vehicle, and they've made over 500,000 of them to date. In 2017, that car received a pretty huge upgrade, and right now, after releasing the Ariya EV, Nissan is working on a refresh of the Leaf. Tesla gets the most attention for EVs, and rightfully so, but many other companies have been in this technology for some time. Oftentimes, they tend to be makers of ICE vehicles, though, so electric offerings can fall by the wayside in terms of development. GM is actually a prime example of this. They first dabbled in electrification with the Electrovan hydrogen fuel cell vehicle in 1966, the Impact concept in 1990, and then really made a splash with the EV1 in the late 90s. This was meant to be the first mass-produced electric vehicle, and it was extremely popular amongst those driving them, and could have put the industry on a path to electrification much earlier, but it was discontinued by 2003. There are many theories as to why this program was shut down, and why these cars were ultimately destroyed, but long story short, GM didn't enter this space again until the Volt and Bolt came about. If you want to see more about the EV1, check out the documentary Who Killed the Electric Car. The Volt was a plug-in hybrid that arrived in 2010 with battery cells supplied by LG, and then the Chevy Bolt was GM's first fully electric car to scale. This was a fairly appreciated vehicle since it delivered a modest range at a decent price. Ultimately, that car was discontinued in favor of GM's new Ultium platform, which is delivering a variety of electric cars like the Blazer, Equinox, Hummer, Cadillac Lyriq, Silverado, and more. Other companies like Ford and VW have introduced EVs in volume over the years, like the e-Golf in 2013, the Focus Electric in 2011, and more. But one particularly interesting vehicle was the electric Toyota RAV4. This car was ultimately a compliance vehicle, meant to meet California's zero-emissions vehicle mandates, and their first edition sold a few units in California by the early 2000s. Then from 2012 to 2014, they actually partnered with Tesla for the second-generation RAV4 EV. This utilized Tesla's powertrain technology and marks one of the only true partnerships on this level that Tesla has had with a major automaker. All in all, a lot of companies have worked in the lithium-ion battery electric vehicle space over the years, but it's only now that we're really seeing every major automaker announce and ship fully electric vehicles in true numbers. It's a very exciting time, and one where we'll see tons of companies expanding battery production and partners beyond Tesla. So just how do all of these battery cells actually get made? Well, of course, every company is going to have some differences, but first, here's a brief explainer of batteries from the US Department of Energy. Quote, a battery is made up of an anode, cathode, separator, electrolyte, and two current collectors, positive and negative. The anode and cathode store the lithium. The electrolyte carries positively charged lithium ions from the anode to the cathode and vice versa through the separator. The movement of the lithium ions creates free electrons in the anode, which creates a charge at the positive current collector. The electrical current then flows from the current collector through a device being powered, cell phone, computer, etc., to the negative current collector. The separator blocks the flow of electrons inside the battery. In general, battery production follows these steps. First, you have raw material sourcing. This includes a number of materials, but the main ones that must be mined and sourced for a lithium-ion battery include lithium, nickel, cobalt, and graphite. In essence, lithium provides the charge carriers that power the battery, nickel enhances battery energy density, cobalt stabilizes the cathode, and graphite serves as the primary material for the anode. Tesla actually goes into great detail about these minerals and their sourcing in their yearly impact reports. Oftentimes, automakers aren't even in on this process since they're sourcing their batteries, but Tesla has engaged in direct sourcing here in the past and is currently working on their own lithium refinery in Texas, which brings us to the next step, material processing. This includes things like lithium extraction and refining, cathode and anode separation, and more. Processed materials are coated onto metal foils to form electrodes, and then those rolls are assembled into cells. For almost all Tesla vehicles, these are cylindrical cells, and within the cell, the cathode, separator, and anode materials are layered. Cells are assembled, and then they go through formation and aging. This involves initial charging and discharging to stabilize the cell, as well as aging to ensure cell reliability and performance. Quote, the industrial process of lithium-ion batteries usually involves 50+ individual processes. Now that the cells are produced, they go through a few more steps. First would be module assembly, and then final pack assembly, both of which happen at Tesla's own factories. They receive the cells from suppliers and then organize them from there. Sometimes as well, Tesla does go direct cell to pack, depending on the vehicle, eliminating the modules. Finally, these packs are performance and safety tested, installed into vehicles, and tested a final time. This ensures the battery pack properly interfaces with the vehicle. One thing to note is that, of course, these processes will be a bit different from company to company and between form factors like Tesla's 2170 cells, CATL's prismatic cells, and BYD's blade batteries. It's actually pretty amazing to consider just how different these cars can look when torn apart, while looking identical from the outside and delivering similar functionality. Each step of this process is optimized by tons of robots today to ensure quality control, speed, and reliability. Then, in the future, developments like the dry cathode should help this process become far less complex and more environmentally friendly. So when it comes to scale, just how much are we talking about here? Well, for 2024, Tesla delivered a total of 1,789,226 vehicles. 1,704,093 of those were the Model 3 and Y, whereas 85,133 were the Model S, X, and Cybertruck. Tesla doesn't break down these deliveries much more beyond that, but clearly we can see how much the Model 3 and Y dominate in sales. They made up 95.2% of all deliveries in 2024. Different studies from Cox Automotive and others, however, give us an idea of how much Tesla is selling of specific vehicle trims, and it can give us a better idea of overall battery supply scale. For each Tesla product, many battery cells are utilized. Exact numbers are tough to come by, but here are some rough estimates. For the standard range Model 3 and Y, there are about 2,976 cells. For the long-range Model 3 and Y, there are about 4,416. For the Model S and X, there are about 7,180, and for the Cybertruck, there are about 1,344. Again, these numbers have changed over the years, and it's hard to nail down exact numbers. So when we look at Tesla's overall vehicle production for 2024, the analyst breakdown puts it at about 60% of all Model 3 and Y sales being long-range vehicles. That would mean about 1,022,456 long-range versions of those cars sold for the year. From there, standard range versions make up the other 40% at 681,637. For the Model S and X, they sold about 46,168 with long-range packs exclusively, and then they sold 38,965 Cybertrucks. If all of those numbers are correct, that would mean that for 2024, Tesla and their suppliers had to produce 6,927,572,608 battery cells in order to sell all of the cars that they did. Almost 7 billion battery cells just to ship Tesla's global vehicles. This is based on a number of estimates and non-perfect numbers, but it is breaking down number of cells between cars and how many were sold. A number like 7 billion can really show you why, as exciting as it is, Tesla's own 4680 production hitting 100 million is fairly small. If we break this overall production down into a time interval, that means that Tesla and their suppliers are making 13,200 battery cells each minute, or 220 per second. But of course, that's just for Tesla's cars. Tesla's energy business remains this ever-growing part of them that nobody really talks about, producing the Powerwall and MagBak. For Tesla's stationary storage, the Powerwall includes an estimated 4,288 cells, and for 2024, they deployed 31.4 gigawatt-hours of stationary storage. This, of course, includes their massive MagBaks, which could include up to 1,238,756 cells per unit if they utilize a similar structure to the Powerwall. It's much harder to find information on the MagBaks, but if these numbers are accurate, that would mean that battery cell production, specifically for Tesla's stationary storage products, actually outpaces their vehicles. This would put Tesla at about 9,973,537,813 cells produced in 2024 in order to ship their stationary products, almost 10 billion battery cells. Breaking that down into a time interval, that would mean production of about 18,960 battery cells per minute, or 316 per second. 316 battery cells, just like that. So adding that to vehicles, Tesla and their suppliers in 2024 likely made 32,160 battery cells each minute, or 536 cells per second. That pace of production is pretty incredible to consider. But of course, it's enabled by multiple companies with multiple factories and multiple production lines around the world. Panasonic was the first company to really work with Tesla, at a time when this level of battery integration was considered quite risky. EVs were a risk, so investing heavily in battery production for them was a risk as well, but Panasonic took on the challenge. Briefly looking back for Panasonic, they were originally founded in 1918 and began making batteries in 1931. Throughout the 1990s, they became a pioneer in lithium-ion batteries, then after acquiring Sanyo in 2009, got much more involved with EVs. In 2010, they invested in Tesla and began supplying batteries from there. At this point, I'm sure that they are quite happy they took on this project and invested. Looking forward, they have many plans for new battery factories around the world to supply future vehicles from many companies. LG Energy Solutions in China did their initial lithium-ion research in 1992 and became the supplier of the battery pack for the Chevy Volt in 2009. In 2019, they partnered with Tesla and have been supplying 2170 cells for the Model 3 and Y at Giga Shanghai and Berlin. CATL, now known as the world's largest battery producer, was established in 2011. In 2020, they partnered with Tesla and they've only expanded from there. They are one of the best-known producers of LFP battery cells, which is a different, reliable chemistry that isn't quite as dense but brings down costs significantly. Their LFP cells supply the Model 3 and Y standard range out of China, and Tesla did use them for a time for standard range cars in the US as well. At this point, it is estimated that they produce about 40% of all of Tesla's Model 3 and Y battery packs. BYD, also known as Build Your Dreams, was established in China in 1995, and by 1998 was the largest producer of certain mobile phone batteries. In the 2000s, they transitioned to lithium-ion batteries and released their own plug-in hybrid vehicle in 2008. In 2020, they introduced their Blade battery and then partnered with Tesla for that battery out of Giga Berlin in 2023. That partnership is particularly interesting since BYD is actually Tesla's biggest competitor when it comes to EV sales in China and across the globe. However, this kind of competitive partnership is fairly common. For example, we often see Apple and Samsung as the biggest competitors in the smartphone space, yet Apple sources their smartphone displays from Samsung. So it may seem odd that Tesla is somewhat funding the company that is taking away some of their sales, but this is fairly common. Lastly, for battery companies, Tesla, of course, has their history partnering with Panasonic at Giga Nevada, but in 2019 they acquired Maxwell Technologies. In 2020, they outlined their plans for 4680 cells and then had produced their 100 millionth by 2024. They plan to greatly expand their Nevada factory for a number of reasons, one of which is expanded 4680 cell production. They actually say that they plan for a 100 gigawatt-hour 4680 cell factory, quote, with capacity to produce enough batteries for 1.5 million light-duty vehicles annually. So Tesla has massive plans to grow as their own battery supplier here. Long term, I actually wouldn't be surprised if we see them partnering with others for their batteries, much like Samsung does to supply Apple with displays, but they have a lot of scaling to do before they get there. Going forward, Tesla plans to expand with all of their suppliers, and multiple suppliers also plan to produce 4680 battery cells. Parts of this design are exclusive to Tesla, but the form factor is becoming popular across the board after their introduction. We've seen this confirmed by Panasonic, LG, and Samsung, showing how this new form factor definitely isn't exclusive to Tesla. It also shows how much Tesla's demand for batteries does shift the market, and what battery supply actually gets scaled. On top of all of these companies Tesla already partners with, EVE Energy, a Chinese battery manufacturer, was recently rumored to have signed a battery supply deal with Tesla. This deal seems specific to energy storage batteries, but it shows how much Tesla plans to expand. In addition to growing supply with current suppliers and making more of their own batteries, Tesla is looking to add another player. This deal could particularly come into play for their upcoming Chinese megafactory that will be making megapack batteries outside of the US for the first time. Nothing is slowing down in this regard, and of course, this raises questions as to what happens to 536 battery cells a second when they do reach the end of their life. I have other videos that go much more in depth on this, but in essence, this technology is still fairly new, so recycling hasn't needed to scale all the way yet. Still, Tesla already recycles their batteries and says, quote, none of our scrapped lithium-ion batteries go to landfilling, and 100% are recycled. Then there are plenty of other companies like Redwood Materials, Li-Cycle, and more getting ready for the future here. Ultimately, long-term, it should create a circular system where these raw materials are fully recovered and put back into future batteries, lowering the need for the first steps of battery production. Then battery technology will keep improving to be lasting longer and be easier to manufacture. Going forward, there are a number of improvements expected for batteries. First is charging speed. Today's EVs often top out with a peak rate around 150 to 250 kilowatts. Overall, a charging curve regarding how long the battery can charge at quick rates is most important, but many are pushing the envelope with charging speed. Tesla is in the process of rolling out faster chargers that interface with the Cybertruck for up to 500 kilowatt peak speeds, and the hope is that this technology will come to their other vehicles in the future. Other brands today offer 350 kilowatt peak speeds, and future battery tech promises to drive this down even further. After that is higher density batteries delivering much longer driving ranges, or the same range on smaller battery packs. In practice, that brings down cost and weight, which improves efficiency and charge times. Then there are longer lasting batteries in terms of cycles and years. Some technology has been in the works that could offer 1 million miles on a single battery pack once it can be scaled. Then there are improvements to affordability, and nobody is ever standing still there. Every piece of this brings down affordability, but a big part of it comes with manufacturing. In fact, Tesla just patented a new manufacturing technique for LFP cells that they say can bring down costs significantly. Ultimately, we want this technology to progress, but there's a reason things move slow when getting introduced by a company like Tesla. As you can see, this operation is extremely complex and literally involves billions of battery cells each year. Tesla and their suppliers made up to 536 battery cells each second in 2024, so it's very complex and difficult to keep this ball rolling while introducing new technologies in the process. Still, that work is underway and it's exciting to see. I'm very curious to see where things go this year and which companies end up making the most battery cells long term. In the meantime, if you want to see full details about all the new battery tech coming to EVs in the future, you can check out that video linked up here or in the description below. Thanks so much for watching, and I'll see you on the next one.